Mic check. Okay, there we go. Perfect. Yes, that's all. That. Center needs. Okay, all yours. Got both of those up. If you can remember to do both screens, that would be awesome. Or I can do that if you. Okay.
Okay, so this is my thing to review. So the chapter 5, we talked about probability, and this is what is pretty much covered in chapter 5. So for probability, it is the frequency over the sample space. It's not for negative, and the values 0 to 1. If it's closer to 1, it's more probable. If it's closer to 0, it's less probable. For multiple outcomes, they're mutually exclusive, complementary, and independent and conditional. Mutually exclusive is where two outcomes cannot occur together. Complementary is where the sum of them equal to 1. If you subtract 1 from like the total, it will equal the other probability. The independent is where the probability of one outcome does not affect the second outcome. And then conditional is where the probability of that outcome depends on the other outcome. For Bayes' theorem, it relates to conditional and unconditional probabilities occurring at random. And this is the formula. It looks messy, but that's how I had added on the computer. The mean of probability distribution, expected value, is that sign right here, and it's just the sum of the values times the probability. The variance formula is that sign squared, and then you just do the mean or the value minus the mean squared times probability. And there's another equation for that. Standard deviation is the square root of the variance, and that's another way to write it as well. For chapter 6, it was more about normal distributions and z-scores of probability. And this was what we had to do, the unit normal table and finding and locating z-scores. So normal data distribution is like your average bell curve. It's the data is 50% above the mean and 50% below the mean. The mean can be anywhere from negative infinity to positive infinity. The area under the curve is equal to 1, and the tails are asymptotic, which means that they always approach the x-axis but never touch. For finding a z-score, you do x minus the mean over the standard deviation. Or you have to look on the unit table. The column A lists z-scores, column B is the area between the mean and z-score, and column C is the area from z-score to the tail. As the z-score increases, area between the score and tail decreases closer to 0. You have to transform what score you get to the z-score in appendix C. For binomial compared to normal distributions, binomial can approximate normal distributions as long as the n is equal to or greater than 2. The larger the n value, the better approximation. Probabilities can be used for estimating as long as the NP and NQ value are greater than 10. For chapter 7, we covered sampling distributions of probability, and we go over the different types of sampling and standard error. For sampling distributions, sampling means on the x-axis and the frequencies on the y-axis. You have sampling with replacement and sampling without replacement. With replacement, the participant is replaced before the next selection, and then without replacement, it's not replaced before the next selection. So I gave like a little example here where I had like 10 M&Ms, and after eating one, I had 9. So then that was like the example. For the mean, oh no, that's not it. For mean with sampling distributions, there's like 3 ways. There's unbiased estimator, random sampling that equals the value of population on average. The central limit theorem is the shape that tends towards the normal distribution, regardless of whatever shape it looks like. Minimum variance is the standard deviation that helps measure the standard error of the mean. For theoretical versus experimental sampling, experimental is what's most common. It has the weird equation with exclamation points. It's where order does not matter and usually has without replacement. Theoretical sampling is the opposite, where it has order matters with replacement, and it has the capital N to the or lowercase n. For standard error of the mean is the standard deviation over the square root of the n. You can also do the z equals mean minus the population mean over the standard error. As population standard deviation decreases, standard error of the mean also decreases. As sample size increases, standard error decreases. If mean increases, standard error also decreases. For chapter 8, goes on hypothesis testing. We went over the types of errors, alpha, beta, power, z, statistic over z of p. So for hypothesis testing, we had to state the null, which is the H0, and the alternative hypothesis. And usually the critical level is 0.05. If whatever value you get is greater than 0.05, you reject the hypothesis, the null hypothesis. To confine the statistic, you do sample mean minus population mean over the standard error. And then you make a decision whether it's greater than or less than. These are the errors. So if it's true, if you wanted to retain the null hypothesis and you were correct, that's fine. But if you wanted to retain the null and you were wrong, it's a type 2. You rejected the hypothesis and it was true, then it's a type 1 error. For alpha, beta, and power, the alpha is the symbol. It's usually 0.05 and it comes into a type 1 error. Beta is type 2. And power is the probability of rejecting the false null hypothesis. If you increase the effect size, sample size, and alpha level, you'll increase the power. If you decrease the beta, standard deviation, and standard error, it will decrease the power. directional versus non-directional. Directional is usually worded as greater than or less than. It's for like one tails. The p-value is not doubled for the one tail test. And then for non-directional, you have two tails. You have to divide the alpha level by 2 to get each tail. And then it usually eliminates type 3 error. So for the effect and effect size, it's difference of sample and population mean in the null hypothesis. It's insignificant when the null is retained. It's significant when the null is rejected. Effect size is the percent of variance explained by variable. Oops, don't look at that. Cohen's d is the measured the number of standard deviations that shift above or below the population mean. When d is 0, there's no difference. And then you can look at this table that tells you if the d is small, medium, or large, and this is the equation for mean minus the population mean over standard deviation. And then I made some memes because I thought it was going to lighten the mood. I just found these on Google. They have like probability, and this one says like Excel versus SPSS. But yeah, that's it. Yeah.
That's awesome. This one. All right, all right. See all the memes.
Oh, it was like the standard deviation for normal distribution or something.
Do you have something to present, Gustavo?
Normal distribution.
It looks like mine is not really complete. I mean, I have like all those slides, but it's not like the complete like review. It's just like I just grabbed like the ones that were like the formula base, basically.
But it does cover all the chapters.
Yeah, basically.
Well, that's the way you reviewed. That's okay.
Well, since because I have the exam 1 review and I put in the exam 2 review.
So this is in the exam 1 review instead of.
So basically, the exam 2 review is as the exam 1 basically. So I'll turn in the last review in the exam 2.
Okay. Well, if I haven't graded, I should be able to see it. Did I grade it already?
Mhm.
Okay, that's why I don't see it. Okay. Exam 3. There's that. Exam 1 review, no. Two. Exam 2 review. So that should be right. Attempt. Do you mean you put exam 2 review where exam 1 review should be, maybe?
Yeah.
Okay. Okay, no problem. Exam 1 review should be right. No, I have an attempt pulled from 622. I don't have anything. Oh, gotcha. Okay. Okay, I thought I put a limited on there, but no. So there's not already a spot to, so, okay. No problem, I can fix that, that's easy. Student resources. In class. So to view, edit. Oh, you're right, Carlos, yeah. So, yeah. Okay, now if you refresh, you should be able to submit. Should be fixed. Okay. Yeah, that's good. Let's work on it. And let's go like screen. If you can remember, Gustavo, to click on both screens, that'd be awesome. I'm just trying to make it so it's easy for everybody to see.
Can I still like, because I need like to put like the terms, can I still like?
You can
edit after?
You just, yeah, you can edit after.
Oh, okay.
The other thing that I could say is if you wanted to, since I think you're the only other person, if you wanted to have it more polished and present first thing on Wednesday,
Mhm.
that'd be okay.
Oh, okay. Because I just put like the formulas basically.
How do you?
I just did like the steps basically, like the main ones basically.
Yeah, that'd be fine. Yeah, you can present this. That makes
Okay.
sense. That totally makes sense. Yeah. Just gonna like this, share screen like that, and then slideshow play. I think it's the same over here. Yeah. I think you have to. Yeah. Yeah, good.
To the prior probability, you need to know the total outcomes. The equation probability is basically the simple space divided by the simple space. Closer to one more probable and to zero more probable, it can be negative, and that's the adding formula basically. So, and that's the multiplication, the conventional formula. So basically, it's so it depends on like the whole like the wording basically. And I didn't like really get the whole base theorem. So
That's the probability.
mhm.
I can walk you guys through the base if you like,
Okay.
when you're done.
Mhm. Chapter 6, formula for population score is Z equals X MO. Well, for sample scores is X meter by standard deviation. They locate where the score falls on the standard normal distribution. Later, find the probability by using the standard deviation rules. Two values. Step 1, compute the z-score transformation. Step 2, find z-score in column table in appendix B, which then log into a column B for the proportions, and to find the proportion between the two scores, you would just add both proportions that are being associated. Locating scores. Step 1, find the z-score that is being related with the proportion that is given in the unit table. Step 2, change z-score to a raw score. And step 3, standard deviation plus the mean. Chapter 8, Step 1, state the null and alternative hypothesis. Step 2, set critical level greater than error is significant, and if probability of obtaining simple mean less than 5%, we reject null. Step 3, compute test statistic. Larger value equals further the sample mean deviate from population mean. Step 4, make a decision, either reject or retain null hypothesis. Directional stated as greater than or less than null. Upper tail test level of significance is placed in the upper tail, while lower tail critical test is placed in the lower tail of distribution. And that one is the chance, the formula. Chapter 7, theoretical sampling formula. And for chapter 7, I just didn't also like get like the whole formulas. Like I didn't get like for me, like the chapter 7 was like the hardest one. So yeah, like I didn't like really get the whole chapter 7 basically.
Okay, so I can,
Mm.
when we work today, I can come around and help
Oh, no.
people. If you're still stuck on 7 at the end of class, I can stay or schedule time, but I can walk through 7 if you're concerned about
Okay.
7. That's no problem.
Step 1, identify the mean of sampling distribution. Step 2, compute and standard error of a mean. Step 3, distribute sample mean. 3, same above and below mean. That's pretty much it.
Yeah. So. Space.
Is our last day the 27th?
Yeah. Yeah. It was really fast. It'll all be missed. Hope to see you all in future classes around campus, but it goes really, really fast. That's why, and I know we're covering a lot. That's why I'm saying let's get through 10 today, 11, and then 12, and then review. So that way, when we get to our last day, we're reviewing, tying up loose ends, and hoping you with stuff. So that way, we don't run into like, oh, we're on the last day. We haven't covered chapters 11 and 12. So, talk about days. Yeah, it's this chapter and then 2 more chapters, and we have roughly 4 class periods left to go over basically 3 more chapters. I'm trying to not give you guys homework or give you time in class, but I'm also trying to cram it in 8 weeks. So, but if anybody is unsure of something or needs to spend any time before the test, I'm totally down. I just gotta know. So. So Bayes' theorem, this talks about conditional, marginal, unconditional. So the U is the unconditional probability occurring at random. So the probability of unconditional probability divided by the probability of the thing happening is equal to the probability times the possibility divided by the unconditional probability. Don't use this a lot, but the idea is that you're trying to see what would happen between the unconditional probabilities and what the probability of those would be. So like, because they're not, the probability 2 conditional outcomes that can occur at random is what you're looking at with Bayes' theorem. And this is the formula for it. I'm trying to think of like another way to like explain it so that it's clear for people. And the idea is we're trying to see, we're making that inference, so we're trying to see like what would happen in the given population. So just to reiterate, it's the two conditional marginal unconditional probabilities. And remember, we're talking about conditional outcomes. That's like the probability of the outcome dependent on another outcome. So if like for example, the cards, like the first outcome, because I took one card away, affects the next outcome. That's what Bayes' theorem is talking about. Or another example we had here was like whether people they were uninsured and what type of hospital they went to. So like the idea of the conditional outcome is like, with the type of insurance, if that type of hospital like they would attend, that would be your conditional outcome. So that's what we're talking, that's what our formula is for Bayes. Does that help? Make sense? Should we walk through a little bit more, anybody? Let's jump into chapter 10. And then, like I said, once we get through 10, I'll give you some more worksheets stuff, and then we'll work as a class or in groups, and I'll come around. So that way we can get through what I assigned on Wednesday, and then chapter 9 and 10. If we have time, we'll do more stuff. Just want to make sure we get at least through chapter 10 today. If we get into 11, wonderful. It'll make the review easier. Just a second to pull this up on both screens here. The exam's due by midnight on Wednesday. 59, 2 attempts, unlimited time. I take the highest test, and I think I'll post an announcement too. Just make sure everybody you're doing the pre-test and the post-test for every chapter, because that's definitely worth points. So. Make sure that I'm screen sharing this slideshow play.
It still shows WebAssign 1. We did chapter 1 like way back when.
No, I was moving that over for if people were behind. That's why. So with WebAssign, because it's a third party, I can't, or it's really complicated, but I can't do like, I can't just give like you an extension, you not an extension. The way to do WebAssign is to extend it for all for it to work. So if it already came in, you're fine. Now, if you have more attempts left and you want to see if you can get a higher score, be my guest, by all means. Okay, here we go. Chapter 10, testing means related samples t-test. Go through those things today. Shorter lecture. Effect size, match pairs, repeated measures. And then, like I said, we have some worksheets. So. Related independent samples. Independent sample, each group or sample is unrelated. Observed only once. To collect independent samples, select you want to from 2 or more populations because they're independent of each other. That's why you select them from more than one population. Select from single population or randomly assigned to different groups. So we're making sure that we get independent samples by using these principles to get independent samples. Makes sense, everybody. This is just basically the conceptually how we would go about it and what they are. If they were related, it would be a problem. It would be an independent sample. Yeah, related. Related or dependent sample. They can be related in 2 different ways. Observed in more than one group, or a matched pairs design experimentally or naturally, or they share some sort of common characteristics or traits. It'd be a related sample. And we have worksheets where I'll give you like some context for what this means and when they're related or unrelated coming up here. We don't have that so far. That's no problem at all. So what might be something that, what might be a group that could be related or unrelated, you might observe, you could think of. Related groups, people that drive Teslas, people that drive cars. Related groups, right? They'd be related in one way or another. You good? Oh, you still, yeah, that's absolutely fine. It's dense. No, it's fine. We have 4 hours. We will get through it. Taught this class a lot. We always get to the finish line and we have about a 2 to 4 hour window of extra time, depending on where we're at towards the end. So it's fine. I'd rather have the pace make sense and have you get it than have you leave confused. So it's 100% okay. You are good now. That's why you're okay.
Yeah.
All right, cool. All right, no problem. Okay, so this is what that looks like. Treatment 1, treatment 2. Most common related sample designs, they're observed 2 times. So maybe we can think about like vaccines, shot 1 and shot 2, and then how they react both times. Related samples. They both got the treatment, they both got the vaccine, for example. Same groups of people. To make sense. Right. So we have 2 types of repeated measure designs. We have our pre-post design. You measure the dependent variable for participants before and then after. Like pre-post design, your pre-test, your post-test in the course. I'm seeing how you do before, and I teach you the material, and I see you do afterwards the post-test. This is limited to observe participants 2 times. You can't observe them more than twice with a pre-test or a pre-post test. Example might be measure athletic performance, sample of athletes before and after training camp. So like what's their skill, what's their athleticism look like? Is it better after that training camp between the pre and the post observation? Then you have something which is within the subject's design. You observe participants across many treatments, but not necessarily before and after. For example, study the effect of exercise on memory. Take memory test after aerobic exercise and again after anaerobic exercise. So see how it's within subjects, it's just slightly nuanced. Does that make sense? It's good, right? Or do I need to go back? Well, back needed. So matched pairs design, participants are selected, matched experimentally or naturally. Again, common characteristics or traits are shared. Limited to observing 2 groups where the pairs participants are matched, different yet matched. Participants observed in each treatment, scores from each pair compared. So we see what happens in the pairs where they're observed one time. So experimental manipulation versus natural occurrence. Match for experimental manipulation. Used in experiments when we want to find the traits or characteristics are used to match. Measure some trait or characteristic before matching. For example, you might measure intelligence, match just two participants scoring the highest on intelligence, and then the next highest, and so on, in terms of how we might look at experimental manipulation. Or natural occurrence, quasi-experimental, matched on pre-existing traits, characteristics, for example, biological twins, genetic matches. That becomes quasi-experimental because we can't really change their biology because they're twins, versus experimental where we would look at like highest, second highest intelligence and matching those pairs. So what does that look like? Kind of like this. Repeated measures design, you have a pre-post design where you're within subjects. Your matched pairs design, you have your experimental manipulation or natural occurrence. So the repeated measures can be selected by observing participants before and after a treatment. Pre-post design or across treatments within the subject's design, matched pairs can be selected through experimental manipulation or natural occurrence. So I understand kind of the concept. I will give you some examples in a little bit here. Related samples t-test that is used to test about this is occurring with two related samples selected from populations in which the variance in one or both populations is unknown. We're going to compare the mean difference between the pairs of the scores to those observed in the sample. And look at the different score, the score value obtained by subtracting the two scores. Related samples t-test obtained prior to computing the test statistic. Subtract the pairs of scores first, compute the test statistic, and then that eliminates the source of error associated with observing different participants in each group or treatment. It's pretty similar to a z-score. So what? Oh, problem. What does that look like? Well, here's our breakdown. We have our there are within groups error, top here. Differences occur within each group, even though all participants experience the same treatment in each of the group. This is the source of error. The differences are not due to having different groups, right here. The between groups effect, we use test this to determine whether the difference is significant. This is the difference we are interested in testing. Here we have a mean of 2 or a mean of 4. We also have our between persons error, which is right here. So differences occur between each participants. For example, person A increased 1 point from group Q to group Z right here. Person B increased 3 points. So this is a consistent change and therefore a source of error. The inconsistent differences are not due to having different groups. So we're talking about between persons here, within groups here, and the between groups effect was our mean. Those are the 3 different places where that can occur. Mean differences, the between groups effect, are the differences we are testing. The other 2 places where differences occur regarded as errors. In fact, they have nothing to do with having different groups. So we're looking at the difference between or within the groups. Hopefully this diagram makes it a little bit clearer for everybody. So we have our within groups, error differences occur within the column of the different scores, even though all participants experience the same pair of groups. This is the source of error. These differences are not due to having different groups. So this is the between, and we have the between groups effects. This is the mean difference score. So we found the difference between the paired scores, only one source of error remains within the group's error. The between persons error is eliminated when the same or matched participants are observed in each group. So here's our within groups or between groups, and then that's basically looking at that just slightly different. Oh, absolutely, yeah. So help. So our formula, or I can go back, you all need me to, just tell me. T obtained value is equal to the mean difference, the mean sample difference, that's at MD, minus the population difference in the mean over the standard mean difference. So MD, sample mean difference, this is population difference. The larger the value, less likely the sample mean difference could occur if null hypothesis were true. Estimated standard error for the different scores placed in the denominator, standard error for distribution of mean scores. So the standard error for the distribution of mean scores is your SMD. And then we just take this and we square root it. This right here, whenever you see that, that's that difference we're looking at. So like this is the difference in your sample right here. So the square root of the difference in the variance. And where we will go through this, I have worksheets that walk us through all of this. So related samples t-test, degrees of freedom is the n difference minus 1 between the groups. 2 assumptions for computer-related samples t-test, normality. Normality, again, that's going to be your normal distribution like that bell curve. And then independence within groups. Different scores obtained from different individuals in each group or treatment. So for example, teacher supervision influences time elementary school children read. So we have a sample of group children. It's one of our examples on our worksheets today. Stage 2 6-minute reading sessions, record the time children reading each session. We record when the teacher is there, when the teacher is not there or absent. And then we find the difference in the scores, difference in time spent reading. If your reading times differ at a 0.05 level of significance is what we're going to ask here based on this data that we're looking at. So we have 220 minus 210. So these are the difference scores right here. Does that make sense, everybody? So we want to find like, are the kids going to spend more time? Is there a difference in the time spent reading with the teachers there or not? And if so, how much is that difference? Remember the 0.05 level of significance, that's that alpha level, and we have to stay there because you do something 100 times, 5 times based on chance, it's probably going to happen. So we want to account for that. The greatest likelihood, we always have the 95% confidence interval, this thing probably does in fact happen. So first we're going to say the hypothesis. Our null hypothesis is is equal to 0. So the mean difference. So we're saying the mean difference in time spent of reading the presence or versus the absence of the teacher, nothing happens. Null hypothesis. So is equal to 0. Alternative hypothesis, not equal to 0. The mean difference in time spent reading in the presence versus absence of the teacher, that there is a difference, something's happened. Next, we're going to set our criteria. Level of significance is 0.05. Degrees of freedom, because there's 8 in our sample. 8 minus 1 is 7. Locate 7 in the far left column of the T table in B2 Appendix B. You should have a critical value of 2 plus 2.365. Maybe we take a moment to locate that and give me a nod or tell me that you're able to locate that made sense. And if any of you would like, I can certainly bring up the table I'm referencing here if you're having trouble locating it. Just tell me and I'll put it on the screen here. But if you know where the Z-score table is, just keep scrolling down, or the one that I posted, until you see that. all have that. Everybody found that okay? Like where that came from? That's not just random. So we take this data right here. The calculations of for the variance of the difference in the scores. So on our left-hand side, we have the difference and then we square it. So the sum of the differences on the left, sum of the differences squared on the right. That's where that came from. Okay, those differences came from that table right there. So we were saying what happened every single time. Then we're gonna have at least this at this point. Okay. So then we compute the test statistic, compute the mean, variance, and standard deviation. The mean difference is that first formula there is equal to the sum of the differences divided by n of the differences. So that's 120 over 8, which is equal to 15. So where do we get that from? Well, if we go back, there's a difference right there, the 120 on the left-hand side, and there are 8 participants. That's where that came from. The sum of the differences right here, divided by 8 is 15. The variance, sum of the squares divided by the differences in n minus 1. So 3,400 minus 120 squared divided by 8, 1,600. Where did that come from? Right here, 400. That was the sum of the squares on our right-hand side, nd minus 1, which was yeah. So 1,600 divided by 3 freedom is 22.857 standard deviation. We just square root it, 15.12. We're going to practice this on our worksheets. So if this kind of makes sense, great. If it doesn't completely make sense, that's okay. We're going to walk through it. We'll do stuff probably on 9 and 10 in worksheets for the remainder of the class. If you fly through it, we'll do chapter 11, but I doubt that we'll probably just do a lot of 9 and 10 today. So. Compute the estimated standard error with the difference of the scores. So compute a standard error, standard deviation divided by n square root of n differences, 15.12 divided by the square root of 8, which is 5.35. And then we would compute the test statistic, which is the mean difference for the t obtained value minus the mean difference sample minus the mean difference population divided by the standard error, the difference in scores. So 15 minus 0 divided by 5.35 is 2.804. Yeah.
So that population, the difference always going to be 0. Like where did the 0 come from?
Oh, that's because because of the x minus m all the way on x minus m. But basically, like, yeah, x minus m. You take the value minus the mean down the board, you get 0 for the original population. Does that make sense? I feel like it's not. Let me see if I can show you that here. That's right here. That's where they came from. You see that right there? The mean difference, that's from our null hypothesis for our population. So because we're saying that it's 0, that's why we're subtracting it.
They didn't do like any calculation to get that. It's just they just said it was 0.
Because it's null, there's no relationship.
Okay.
We're going to practice too on the worksheets. I feel like you're saying, okay, it's kind of making sense, but maybe not entirely. So then we're going to make a decision to retain or reject the null hypothesis. And we're going to reject it because it's outside of that 2.365 that we found earlier. So that t score versus, or the t statistic versus the t obtained value, just like the z statistic versus the z obtained value. So we make a decision, T obtained value is 2.804, that exceeds the upper critical value. So that falls in the rejection region. So the decision is to reject the null hypothesis, which was, if you remember, no relationship. So elementary school children spend significantly more time reading in the presence of the teacher than when the teacher was absent. Because 2.804. Because it's outside the rejection region. Does that make sense? Or mostly? So another one we can look at, or I can wait, make sure you all have that. Independent variable age, older or younger twins, dependent variable introversion, more or less introverted. Sample 7 pairs of identical twins. Scores 12 to 60, higher each equals greater introversion. Null hypothesis, the mean difference in introversion scores between older and younger twins is 0. We're going to use a two-tailed test at a 0.05 level of significance. So we're trying to see what introversion looks like with older and younger twins. We have these scores right here, and then we get our difference in our scores right here on the right. So, standard hypothesis. Null hypothesis is no mean difference between introversion. Mean difference in introversion scores between identical twins, so not equals alternative hypothesis. That's why it's two-tailed. Level significance 0.05. Degrees of freedom is 7 minus 1. So we had 7 pairs to get 6. So we're going to locate 6 degrees of freedom, two tails in table T in appendix B, and you should be able to find the critical value of 2.447. Everyone find that okay? Literally going to be practicing this today. So compute the mean, variance, standard deviation for the different scores. So we do that formula. The 7, sum of the different 7 divided by n different 7 is equal to 1. Some of the squares, which is 539, which I'm sure we have from squaring those. Minus 7 squared, divided by 7 is 532. 532 divided by 7 minus 1 is 88.67, which is our variance. We're going to do our standard deviation by square rooting that, which is 9.42. Go on the standard error, which is standard deviation divided by the square root of the n difference in scores. 9.42 divided by square root of 7 is 3.55. And then we compute the test statistic, T obtained value, mean difference, sample minus mean difference, population 1 minus 0, over the standard error for the difference in the scores, 3.55 is 0.282. So the sum of the difference was 7. So the square difference was 5.39, was 539, which that came from. We square the differences. Make a decision. Well, we got T is equal to 0.282, bless you. So we're going to retain the null hypothesis because it's under the curve. It's in between plus or minus 2.447. So we retain the null hypothesis because it does not exceed the critical value. If it's right on it or above it, then we're of course going to reject it. So that's just to reiterate, T obtained value 0.282, does not exceed critical value, does not fall within the rejection region, we retain the null hypothesis. There are no significant differences in introversion scores between older and younger identical twins. So it's equal to 0.282, P is greater than 0.05. So we have Cohen's d, ETA squared, omega squared. Cohen's d is the most common measure for effect size used for t-tests. D measures the number of standard deviations, mean difference scores shifted above or below. Population mean difference stated in the null hypothesis. Estimated Cohen's d is the mean difference over standard deviation. We're going to walk through this in a moment. The worksheet. Then we have ETA and omega squared. Estimated proportion variance, independent variable explanatory treatment, two measures. So for ETA squared, N2 is equal to T squared divided by T squared plus the degrees of freedom, or omega squared, which we use W2 for that, T squared minus 1 divided by T squared plus the degrees of freedom. The calculations are the same for all the T tests. I have this on a worksheet where I give you numbers and you can plug it in and look at it on the formula. So for example, if we plug that in, I can wait, make sure everybody has everything. Calculating W2 for example 10.1, we already got the 2.804. That's our T, so we know that's our T value. So we're just going to square that minus 1 on our numerator. And then we're going to do the denominator 2.804. The second power plus 7. So we're going to get 0.46. That means there's a 46% variability in time spent reading can explain by whether or not the teacher was present, which is a large effect size if you look at table 9.4. So chapter 9 and chapter 10 are linked to each other. So some of this should feel like review. Some of this would be slightly new for you. Why should we do this? Well, many advantages, but we're still writing stuff, so no problem. It might be more practical, better way to test your hypotheses. It's more practical to observe the behavior of the same participants before and after some treatment, which are your repeated measures, or to compare how well participants of similar ability master some task. So we might use matched samples. Computing differences in scores prior to computing test statistic eliminates between persons sources of error and reduces the standard estimate of the error. Also, selecting related samples increases power. Reducing the estimate for standard error will increase the value of the test statistic. So we get a little bit more accurate when we have related samples. So how we report it, related samples t-test, report the test statistic, degrees of freedom and p-value, summarize the mean and standard error or result of or standard deviations, measured, figure, table, and results. Not necessary to identify the type of t-test computed, typically reported in results. That's how we talk about it per APA. And that does take us to the end of the lecture. So the next thing I would say, I think we have a pretty good sense of time would be, not sure how you're all feeling about 9. We can do a little bit of that. What I was thinking is I will unlock and make available here and talk to you about what worksheets we're doing for chapters 9 and 10. And then we'll just maybe as a class decide what makes the most sense, whether we're walking through stuff together, give a little bit of time to work, or we do everything together. If we do everything together, which we can, we could run out of time. So it just kind of depends on what makes the most sense for you all. So give me just a second to make that available, and then I'll show you where it is in Blackboard. This is right here. Yeah. Good. It's gonna be 22. Submit. Great. That's right. Okay. Submit. And let's make this available. All right, and then this is what I want right here. And 10. Okay, perfect. Okay. So where we should be in terms of worksheets, and this is great because we have like 3 hours, so we can work together. Is we should be doing, last time I assigned this, right? We did chapter 8, and all that. It was right. So we did chapter, I think chapter 8 review. And then it's chapter 6, 7, and 8. And then it was a part B. Yeah, so it was chapter 9 review. I think we started that one. So it would just be, so it'd be this from last time and chapter 10 worksheet right here, the review. And then it would be also student resources. This right here with today's date. This is chapter 9 and 10 in class review. So it would be this last week, over the answers, etc. For you a chance to work in groups. So basically, it would be 3 worksheets. We want to get through all 3 of those today, so I can do whatever's going to make the most sense for people. We can give you a little bit of time to work autonomously. I can come around, answer questions, and/or we can walk through worksheets one by one. This is basically chapter 9 and 10, just sort of conceptually. The chapter 9 stuff you already saw last time, and then I have this right here, which is not that. You already saw that. It was right here. And then chapter 10, this has a bunch of scenarios. This is literally what I walked you through, and then some samples that are very similar to what the slides talked about, with basically an example, and then when you do it on your own. And then I have an SPSS assignment right at the end in 10.4. So like I said, we can walk through all of everything one by one, or we can start with where we were at. The only thing is we may or may not get through everything because of time. We might. Just kind of depends on your questions. Do you guys want to start where we left off then? Okay. So I believe we left off on this, right? Then part B, and we're on the chapter 9 review, right? We left off on this, I think. Owens D and the t-test. So, and then do we have, did we end up doing the SPSS? We did not. Okay. Okay, so let's walk through it. Okay. I don't think we even walked through this at all. I think I just assigned it, right?
You assigned this. Started chapter 8, chapter 8 is the worksheets that we started.
Gotcha, that's right. Okay, so we can go over chapter 8. Does anyone, you guys want to go over chapter 8? How are you guys doing? Does anyone need a break? We're about an hour or so in.
Like I need to for part 2.
Okay, let's start with that. That's right. Here. No, it's not right. That's right here. Not this one, right? Worksheet 2. So I know we did a chunk of this one. I feel like we did this one.
Yeah, the part 2, I think, is when we create. Yeah, we did some of it. Like the chapter.
Okay, so tell me what's gonna help you all the most, okay?
I don't even-
We can do 8, 9, and 10 today. We probably have time. We have 3 hours. It just depends on your level of questions. I'll walk you through any or all of it. I just want to make sure we're on the right page. So you're saying we did not do any of this?
Wait,
No,
is that the one where we
so
put the
that's
pictures
chapter-
in?
I think we did. I think we did this.
Yeah, I need the last 2 questions. Chapter 8.
Okay.
Chapter 8. Yeah, so you're right. We did basically do that. I just have it.
Okay. Oh, create your own. And then to do this one, right? Okay. So why don't we let's do this one as a group. Because it create your own is kind of like create your own. And then I can maybe come around if you're having trouble creating your own and walk you through that. And then we'll look at the other chapter 8, if anything we missed, and then we'll do chapter 9 and 10 worksheets. Depending on time, if I can get you through all of it, I will. All right, so on your own, calculate the following scenario. Is that even large enough for you guys to see? That is statistics 2. Okay. Chapter 8. That's right here. Chapter 2. All right, share screen. Desktop, Word. No. Window. That's not right. There we go. Okay, so we're down towards the bottom, I think. All right. Suppose elementary school children, general population math scores of 55 plus or minus 7 points on a given math test. Select a sample of 30 elementary school children and the math emergent scores, record a sample mean of 64. Then compute the one sample z-test at a 0.05 global significance to determine if the math emergent program was effective. So this is a directional test. And we're literally gonna do our steps from the example above. So step 1, let's just grab all of this and then let's go through and make sure we're doing that. State the hypothesis population mean is 50. Is that even right? Let's see, we select a sample of population mean is 55. Population means 5, which is really alternative. There's at most 55 points in the population. 55. Yep. that's right. I guess the alternative is greater than the value, 50 plus or minus. Okay, so that makes sense. So we're trying to see whether or not the new sample, if there's a mean improvement. So we're going to start with the original sample. So mean population, we're testing whether alternative is greater than this value. So the null hypothesis with the math immersion program, mean improvement is at most 55 points in the population. Alternative mean improvement is greater than 50 points in the population. Notice the key change for one-tailed tests. Null hypothesis encompasses outcomes in all directions that are opposite of the alternative hypothesis. In other words, the directional statement is incorporated into the statement of hypotheses. In this example, math immersion scores in the speaker's native language is intended to prove math scores. Therefore, a one-tailed test is used because there's a specific expected effect, because we're saying that it's at or above. Does that make sense so far, everybody? We're just doing the null. So the next thing we do is set the criteria for the decision. The level of significance is 0.5, which makes the alpha level 0.5. Determine the critical value for the probability. Appendix C, score associated with it is between Z 1.64 and Z 1.65. So that's going to be the same for step 2. 645, because it's between the two Z scores. Yeah, on the graph. Yeah, that's absolutely right. So drawing that'd be the same thing. Yeah. Then let's see. Then we're going to compute the test, the Z statistic. So bring this down here. Then we need to look at our numbers here. 5 divided by 30. So that would be the standard deviation, which would be 7 this time, divided by 30. 7 divided by 30. Does everyone know where I'm getting that from? So if we go back up, so the Z statistic, so we have this, and then 5 minus square root of 30 equals 0.91. And that was because up here, we took our standard deviation right here, divided by 30 for our sample. So the standard deviation divided by the square root of n. It's the same thing with here. So 7 divided by the square root of 30 would be what? 1.28. So everyone know where I got that from so far? All right, so then the next thing we do is we go back and then we compute the Z statistic by substituting the values of the sample mean for the Z obtained value. So we're going to take this. We're going to bring this down here. Sample mean, I don't think it was 60. What did I give you? 64. So the mean is equal to 64. 64. Talk about the null hypothesis. Which is 55. And the standard error we just calculated, which is the 1.28. Does that make sense, everybody? So now we're gonna do the Z obtained value, which is the formula on page 256. So we're going to take and plug these numbers in. And then we don't know the decision yet, we'll know in a second. So it's not, it's gonna be 64 minus 55 divided by 1.28. Then we have a number right here, right? What do we have? Equals 7.03, because 7.03 is greater than the critical value. We know the scores in the math immersion scores and the native language improve the scores. Decision is to reject the null hypothesis. And then the last one is create your own for that one. Does that make sense? Literally just plugging in the new data into chapter 8. And then the last one, all you would do is create your own, or what you could do for anybody. You could literally just take something like this paragraph and then change your numbers a little bit, like make a different mean, make a different standard deviation, and then change these and then just walk through it like the same way. So like if you don't want to do a completely original one, you could just take like this one and then you can say something like the math scores show 60 plus or minus 5, and then you could do a new mean improvement of like 70 or 73 or something that's like different, and then you just plug it through the steps again, and that'd be how you create your own. Does that make sense to everybody, I hope? And then the next thing I think was something else in chapter 8, right, Carlos, or anybody else? Or are we jumping into 9? I just want to make sure we answer all our questions and help. Chapter 8, okay, so you're talking about this right here. You mean the SPSS thing? Because we did that last time. Part 2. In your own groups, you come up with your own hypotheses. And then you walk through the steps based on
Is that one the one where we had like difficulties on the?
that was when we had the problem with the SPSS at the end. But you know what we can do? Just for time's sake, and because I'm the boss, how about we just cut out part 2 completely? How about I just completely say that that's not required? But you got to do the SPSS part. Okay. How about we just completely eliminate all of this to part 3? Okay. Yeah, just less work. So now we can do chapter 9. And you have less stuff to do. Yeah. This was chapter 8 worksheets with stats. What I'm saying is, rather than do part 2 where you got to list your own hypotheses in groups, just do that first thing with the power exercise, which I have the answers I can walk you through once you have them, or we can walk through this as a class.
I'm trying to remember. So I'm trying to like find this.
We did walk through this, right, everybody?
Yeah, we did. It's 7, 11, 26.
So 11, 22.
It was.
Yeah, and then it was wonky. That was the one. That's the one that has a problem on purpose, so that you can. So if you got a curveball at SPSS, you would know what to do. So that was not so much like understanding this test. More like, why is the data not working? And then what we had to do is we had to open an Excel file, and then once we open the Excel file, we had to open it as a CSV file.
Yeah.
And then the import was correct, and then we ran those, then we just did the drop down, and then it
So then now we.
gave
can
us
put
like a really
everything
nice
in.
chart, and then I said, just save it.
Yes.
And I didn't say like, explain what that was, it was just more of like, here's a random problem, here's how you fix it with SPSS.
I think make sure I submitted it, 'cause I remember doing
You
it.
should have a really good time to submit.
Oh, we're-
I'm trying to fix my code.
we did it on here, so.
They just do it in the back.
And it's just easy.
Okay.
Wanted to start a new, where we're doing our old files that we turned.
So if you do a submission, I'll be able to see multiple submissions. So for this particular class, it's set up as unlimited attempts for all the assignments. So if you want to do 5 submissions, I'll see all 5.
Yeah.
So it won't delete it, but you might not see it, but it'll like, I'll see it.
Because I turned in the SPSS section.
Okay.
And so I want to also turn in the part one, did all the work, did we got the student deviation of 20. So I'm scared it's starting the.
No, starting is not gonna mess up. And if you want,
Right.
before either when we're working in groups or whatever today, I can take a look at my computer and or thing your schedule. Right after class, I can look and just make sure that it's all there, just because I don't wanna like
And then you do the
broadcast and just grade on the screen or anything. But yeah, it's probably there, but I can make sure. Yeah. Everything working over there? So if you're all in a pretty good spot, we can jump into 9. How are we on time? Or we can do 9 and then take a break, or a break now if you need one. Yeah, what's up?
But we're doing minus 1 for the increase. So if we're at 18, so that's how we get. Plus or minus 2.110. So those are our 2 scores that we have to see above
I do feel
or
okay,
below.
because
So then, but.
Only issue is just making sure you get the.
Right, and I'll show you what that.
basically,
So
You see it
then
as
he added all that
CSV
together,
file
then
in
he,
Excel. and then you
found
go
that
in and
his
you
mean
import Excel.
was
and you go
62,
drop
so
down
then
to like,
you
say
compose
CSV.
squared
And
it,
of course, then you
divided it
do
by the whatever he rolled, and he got his standard deviation of 20.9.
Save it as a CSV,
Now we
but
can plug it all
open it as an Excel
So
file.
just like his
And then there will be a
previous
drop down as
picture,
you're opening it,
uh,
open it as
here.
CSV, but don't say CSV
You wanna
file, initially
go
say
to the
Excel
standard
and
deviation
CSV.
square of.
And then that'll fit, that it'll truncate the data to
The
a
standard
smaller.
deviation square root.
And you're just gonna go through and say.
That's
okay,
your
everything.
standard. error.
And then when
So
you
you get
run the
4.94,
steps that are
right?
in there, which I think.
So
I
then
recorded
that's
those
our-
as well.
Oh,
Then
yeah.
you plug it- then you
On-
plug those in
on-
because,
on which
you know,
ones to do, and then
examples that we
it
have,
should,
take
be-
minus
you get just a relaxed place table. It'll just save. Okay.
whatever
and
you're
a
testing,
save
so
file,
doing
we
the
just look at data and it has to be
7.7 yeah,
So then I'm gonna
So
just make
he
sure that you got
subtracted
both
that,
pieces of that. 'cause you-
and he
you know,
divided it
data.
by. Bless
Bless
you.
you.
Okay.
Excuse me, he divided by the
Escape.
square
I have
that we
2
got
questions.
when we square root.
The first question, I
So
didn't
then
exactly
he
know my 9,
Yes.
because I thought it was
So
that
he
we were
realized
supposed to
that
every
it
9
was
today, so I didn't
the
really do
non-
it, not knowing, and he got a
Yeah, I can do that.
Rejected the
that I
So then he said,
submitted
now
a
use
request,
this
but
sample,
my
plug
second
in
question is for
on
the
the same
second 9
process. So
worksheet.
I just did all that.
So I don't know where to
So-
find my T of T
So now we're here.
Like
We're still
I got my
using the
phone
same stuff
T
that we
value.
did, minus 1, so it's 20.
Oh, for chapter 9, we're gonna walk, I'm gonna walk through that.
We
We'll
find
do
the
all momentarily,
appendix.
step by step, so I'll probably answer that automatically, and if I don't, you just gotta tell me. But, so we're gonna walk through it.
Because like the ETA.
IT,
Oh,
I
there's
got
like
the
a
still
still
like
like
so
so new, I don't
So
know
we're
where
looking
they
under
have
0.05. Just like
I
we did on
think
9.
the next
So that's
worksheet,
our-
we're really gonna walk
well,
through
our,
all the T
critical
values, as well as ETA and
And then I
omega,
gotta copy that.
on the worksheet we want ready to do.
Okay.
Momentarily. That should clarify, if it doesn't, just talk.
Okay.
Was there another question?
No. Yeah, that's my answer.
Okay.
Where are you at right now?
Okay, so like here. So then we got 21.92, so we're now in the plus or minus 2.093, right?
Yes.
So then
I
we
think-
plug in the
I
answer,
was
I got
already there.
4.90, and then I did not do this part.
Yeah.
Yeah.
Yeah, that's fine.
That's what I'm trying to figure out.
So
And then just,
plug everything in,
just-
so we
and
have
then
60.
just plug those
That's the
in.
code we have.
And
They
then
measure
repeat,
90 by 400. Okay, wait, where are you on this worksheet? I think it's very end.
No, I meant the beginning still.
Yeah, so then take a picture of it
So that's negative.
and upload that. As long as it's all there, this is 2022. Like I will take photos of your handwork as long as it's there.
That's way beyond.
As long as I can read it, just don't like.
Wait, go to your data real quick.
So this is where I'm at.
Okay. PNG or
So-
whatever.
Your worksheet looks so different.
This is
than mine.
his, it's because I color coded. So this is his example here above.
Yeah,
So I
yeah.
just copied
The
that and I
7.03
put it
is
in. So
correct.
our mean
And
is
then
60,
The
population
last
is
one
2,743,
is like I'm saying, create your
our
own.
N is 20 and our
So it's
ST is
whatever
not
you guys
20.
create.
So
do the
I
same
plug that all in.
steps.
Oh, so, cause like if you scroll down a little bit, you have them on your color palette. Yeah,
Well,
yeah,
That's here, but I haven't
But
copied
you
it.
okay, but I feel like that's like every time.
Probably, but I haven't even like scrolled all
So
the way
the
down
critical
yet.
value is C obtained value. Is equal to the mean.
Where? TFJ?
um,
So it's 60
Minus the
minus
other mean,
7,
sample. The sample mean
divided by
minus,
our
minus
standard deviation.
the 30 divided by the standard deviation. The mean minus the mean over the standard deviation.
Is that an equal negative
Which is
3.8?
3.
So it's beyond, because it's past.
Here's the
the
obtained
2.0.
But if you
It's like-
if you scroll up though,
It's
like
way.
in the steps, it
Yes,
is
the-
the exact same thing. So if you look at like where I floated it
Right.
from,
That's
in
the
the
one,
lower
it
that's the
literally
thing
will
here.
walk you
Yeah.
right through that.
So it's in the lower tail, right?
Listen, I gotta catch it. Divided by the square root of-
But a lot of it I kept the same to keep it easy. So
Which was.
And then I also have the notes of like, where if you scroll down, it even tells you where I am in the textbook, what formula, what page in the textbook.
It's 70.
Oh, I didn't do it. So I mean, it's
17, right?
only 1, 2 divided by this. What?
Wait, wait.
Which is the standard
Standard
deviation.
mean
divided
is
by
your
the
standard
square root,
deviation, not the mean, yeah.
Right? It's whatever you did with your new. Yeah, no worry, yeah, there you go.
Yeah. 4.1.
But make sure you do the math because your
Cause
numbers. are gonna be
mine, I got
different.
20.02 on mine, so.
What I'm trying to do is
20,
really about like every
That's
step,
0.02. That makes sense.
so then you can literally replug the numbers in,
What did you do, Mary?
you do your own, so that you don't. You can,
That's what just
you can type in
sounded.
like
Did you do it? by-
scientific calculator on the internet. You can probably give me something to just use. Yeah, no problem. So everybody ready to jump into chapter 9, like a worksheet? Does that make sense? All right, let's jump in. I think we were right about. this one. Chapter 9 and 10. Would be- no. This one, I think. Chapter 9, right? Chapter 9 review. I'll send chapter 9 till like Wednesday at midnight.
I was gonna do it like by the end of tonight, so
Okay.
whatever's fine.
Yeah, I can do that. Or yeah, I can do like by tonight or by tomorrow or something on chapter 9.
I have to do one with my attorney later this week, so.
Yeah, I can do something like that. Yeah, I can give you like an extra day or two. That's no problem at all. when you request it, I think, because I have to click on website to see your request. But from Blackboard, so I don't think it like emails me, but I can, like I said, I can extend that for everybody,
Okay.
and I can do that pretty easily. All right. Make sure that I have the right chapter 9 share. Okay. All right, so let's zoom in, not that much. All right, the estimated standard error is an estimate of the standard. Do you guys need a few minutes? Okay. The estimated standard error is the estimate of the standard deviation of the sample distribution of the sample means selected from a population with an unknown variance. It's an estimate of the standard error or standard distance that the sample means deviate from the value of the population mean stated in the null hypothesis. The T statistics, which are known as T observed or T obtained, is an inferential statistic where we're going to draw meaning used to determine the number of standard deviations that a sample mean deviates from the mean value or the mean difference stated in the null hypothesis. The T distribution, or student's T, is a normal like distribution equal to the degrees of freedom for sample variance for a given sample n-1. Each T distribution is associated with a specific specified degrees of freedom. As sample size increases, the degrees of freedom also increase. FYI, the degrees of freedom for a T distribution are equal to the degrees of freedom for a sample variance n-1. The T table lists critical values for 6 levels of significance for 1 and 2 tailed tests. 3 assumptions for a 1 sample test are normality. Normality, again, regular bell curve, random sampling, and independence. The outcomes are independent of each other. The 1 sample T test is a sample statistical procedure used to compare a mean value measured in a sample to a known value in the population. It is specifically used to test hypotheses concerning the mean in a single population with an unknown variance. All right, example 1. So we'll walk through example 1, and then we'll either do the next one as a class, and or I'll give you a little time to work for a few minutes as a class, and then we'll go over the steps just so that learning. What was that? Oh, sure. Yeah, absolutely. Yeah. Yeah, I'd be happy to whiteboard. Social functioning is the ability for the individual to interact or adapt in a normal or usual way in social environments. The area of research is of interest to behavioral researcher, particularly in the medical or clinical settings, and those who study human development. Should say sample. I don't know why that's that. Because you can have your degree from here or anywhere else, but if you don't have any social skills, you can't interview well, you're not going to get the job, homie. It's not going to happen. You got to have social skills. That's important. An example for the use of a 1 sample T test. Asked relatives in the population with obsessive compulsive disorder are as healthy as those in the general healthy population. In their study, they recorded social functioning relatives of patients with OCD using a 36-item short form health survey with scores ranging from 0 worst possible health to 100 best possible health. They cited that the mean social functioning score in the general healthy population of interest was 77.43. Using the sample data below that approximates our findings, we will test whether the mean score in the sample data given below significantly differs from the general population of a 0.05 level of significance. These are our scores that we're looking at. That's all the scores. So let's state the hypothesis. The mean population is 77.43, and we're testing whether or not, if it's equal or not equal to the population, mean differs from the sample mean. So null hypothesis, H subset O, U is equal to 77.43 for relatives that care for patients with OCD, care patients with OCD. The mean social functioning score is the same, right? As that in the general healthy population, the same as that in the general healthy population. So then we want our alternative hypothesis for relatives who care for patients with OCD. The mean functioning score is not equal to 77.43. Is not equal to 77.43. Do these have a null alternative make sense? I can write that out. This is basically the same as this, not equal to. I can write that out if that'd be better, just tell me. It's also on here, we're looking at this, right? These are our two hypotheses. Next step, we're going to set the criteria for the decision. The level of significance for this test is 0.5 alpha, 0.05. Because we have to factor out for chance. We're computing the two-tailed test because we don't know. We're just saying something happens. It's not equal to. We're not saying it's at less than or greater than. We're saying it's just not equal to. That's why we're doing two tails. Make sense? Okay. So n is, we are computing a two-tailed test with n minus 1 degrees of freedom. So n is equal to 18. So everyone know where we got 18 from. That's the no. I'm sorry, for a row. Yeah, there's 18 scores. So we're gonna get the degrees of freedom. Remember, degrees of freedom is always going to be, degrees of freedom is going to be equal to n minus 1. So 18 minus 1 is 17. So now we're going to look at the critical values we find in table C, in appendix C, and go to the column for 0.05 proportion two tails combined. The critical values you should see plus or minus 2.110. Does everyone see that in the T table? Make sense? Nick? Okay. No, I'm just making sure it's what I'm explaining is making sense. I'm not losing anybody here. .110. And you should be able to see that in the chart, or at least know where to look in the chart if you don't see that immediately. So the next thing we're going to do is for a graphical representation, what we're doing, look at figure 9.2 in electronics text or page 281 of the paper text. That's just telling you where we're at for a representation, what that looks like. Which I can totally draw on the board if you would like me to, just tell me. Okay. Just gonna double check. Should be right here. 0.4. Yeah. And then we're deciding right here, the 2.110 negative, 2.110 positive. This is going to be retain. It's going to be reject. Reject. So we're gonna have the decision. Yeah, there we go. I want this one. So this decision to reject the decision to reject null hypothesis, or you could write it like decision to reject that, because that's where it happens here or here. Otherwise, we're going to retain. Does that help draw that out? Makes sense. So what we're going to do is so we have our t value. We're going to figure out what our t obtain value is now. Step 3, compute the test statistic. In this example, we compute the sample mean and the standard deviation for the data in the table as in chapter 3. The sample mean is the sum of all scores summed. So the mean is equal to 62. So that would have been, so the mean would have been the sum of all the values over the end. That's where I got my mean from. So if we took those into Excel and said sum and then divided by 18, we would get that. Should get 62. As introduced in chapter, are you with me so far? Makes sense? As introduced in chapter 4, to compute the sample standard deviation, first subtract the square and square the difference of each square from the sample mean, and then divide by n-1 and take the square root of the standard deviation, which is equal to 20.94. So I saved you some time and some steps. Does that make sense so far, everybody? So then we will compare the sample mean to the population mean stated in the hypothesis. So that originally was 17.443. To find the t statistic, we first compute the estimated standard error. To compute the standard error, which is the denominator of the t statistic, we divide the sample standard deviation by the square root of the sample size n. So in this example, standard deviation is 20.94 and n is equal to 18. So we take, for the standard error, standard deviation divided by the square root of n, 2.94. So standard deviation divided by the square root of 18 is 4.94. Does that make sense? Or maybe check, or you can certainly check my math. The formula is absolutely correct. So then the next thing, or I can wait to make sure everyone's with me here, is we're going to figure out the t obtain value. The t obtain value is the mean, the sample mean minus population mean divided by the standard error. But we have all that. 62 is our new mean minus 77.3 divided by 4.94, which you just calculated, which is negative 3.126. That's over here. So what are we going to do? We're going to reject the null hypothesis. It happened to be on this side of our tail. So make a decision. Since it falls beyond the critical value in the lower tail, it falls in rejection region. Decision is to reject the null hypothesis. So the next thing I'm saying do, which I think just for learning, it would make the most sense to give you like maybe 5 or 10 minutes to work on this next one on your own, and then maybe go over it and see if your calculations are correct and everything, is to take these scores right here, which I can scroll down. There are 20, so your n's going to change. That's going to be important when you do your calculations. And then show the same steps right here, and then tell us what you're going to do. And then we'll work on Cohen's D. We're just going to do, so we'll just do that. It is 10:58, so we'll say like 11:05, 11:10. If you guys, what we could do is we could take a break either after that or during that time, whatever, after. So let's do that, and then we'll walk through that, and then we'll take a break after we review, and then we'll start working on Cohen's D, and then the ETA, and then the W2, and then we'll jump into chapter 10. So we're still clipping along just fine. Makes sense, everybody? And like, as you're walking through it on your own, scroll up and just kind of plug the stuff in. It should be pretty straightforward.
Yeah.
So we did ours. So isn't here, ours was a little bit further down to the left, it's in the rejection region. So all that's rejection, all that's rejection, all this is taken. If it was closer to the mean in the middle, then it would have been retained. So because it's far out, it's far out. So that's how he got it, and that's kind of accepted as it. So we did reject the null. So then that's his scenario, and then we plug in ours. And we got negative 3.80. So then we just colon.
One to n minus mu.
Yeah. So then we took. And then ours is negative 0.4, which would show that scores 0.44 is below the. So no. Yeah, so his, I think it ends up being positive anyways, but that's ours. Now, it's wrong, I just-
And then where do you want to save it?
that's exactly what we did.
Change that to a CSV file.
Correct.
Yeah, that's, yeah, I guess.
So we're -1.
It's more than one spot, yeah. Let's
Save.
save. And then when you open up Excel, you open up and ask it to tell it to import Excel, so file for data. Then it goes Excel, and then you're gonna do a CSV file. Then you're gonna go long file. Yeah, just look through the stuff and then do the cross tabs, then.
Yeah, 0.4. That is our. Changing color, that's the only way I can do it. That's another exercise.
So you're
Another
using,
exercise that is just as
so you're gonna use the new table. So
So
you're gonna still do 77.43. That's fine.
Yeah, okay.
Like, so you're gonna still use
Let's
your.
go into 9.6 then.
But then you're gonna. Yeah.
Does that make sense?
Like you're.
We're still gonna be kind of-
You're. And then you're.
Oh,
So we based on
okay.
that. So
Wow.
then you're just gonna. I would probably do Excel,
This?
because you're literally just doing this, you're just literally doing the same steps. But putting new stuff in. But like if you wanted to like. do
Okay. Oh,
Something like
I
mean,
guess so.
a square root or something, Excel. would
Here now,
probably
I'm
do
saving
that.
this last inch.
And I'm gonna walk through this, I just want to give you a chance to walk through steps. So that way.
It's just like, I know, it's all plugging it in.
Raise your hand as long as you've done before I explain it. And
You have it in
do your
chat.
best to-
Yeah, which is this.
Gustavo, are you good? It's a no. This one you probably don't need SPS S4, but you can if you want to check your work or
Oh,
something.
really? Oh,
The
sure.
directions said when we had it on, but that's just-
It's a job answers, I think, it says this
Oh.
makes us focused.
If you're already to that point, keep going. That's fine.
Hey,
That's fine.
hey.
Yeah, if you guys are working ahead, that's fine.
Yeah.
Okay, that's totally fine. Yes. Questions, and I'll go over it in a few minutes.
And that one was the one that we.
It says going data.
We got, but the data's from our, the worksheet.
Okay.
15,
61.
I clicked this one. 65, 83, 64, 66. Fifteen.
You can copy paste it.
Forty-six, 54, 55, 83,
65 or 80?
65, 83, 67, 85, 92, 53.
And then compare these. And then one sample t-test. In the dialog box, select variable. How will it make choose this variable to the test variable? Alright. That's value box is set by default. Type in a value 77.43. Select OK or select Facebook. Hey, look at that. Looks like this. That's it. Hey, that was
That sounds so different.
About 20 points here.
Oh, no. Okay.
My numbers are just a little off from yours. maybe it's a fill down error.
It could be a fill down error.
We're not far off, we're just like 10 off.
Now it's just.
Unless I didn't
Because
ask
I did
that.
Excel too.
I didn't. I used to.
So I just been wrong on that.
No, I mean, it's not far off, like my,
Oh, I know why.
60.
I don't want it.
Oh.
Does that change it?
Well, your standard deviation is still 0.04, not 0.02.
We had our sum of the
What were these?
values of 1200, not 1185.
Then, because didn't add the 15 then, I bet you if I redo this. Let's get rid of this. I bet you if I add all this again.
Maybe it's the misspelling.
But maybe where all my values. Are. Because I feel like I wanted that to be 1200 when I created it. It's all the scores. $1,200.
Yes. There we go.
So Excel lied to me. Okay. So now we have that.
What was the issue? On your thing.
It wasn't highlighted or something. I don't know. It just, it might have been a full down error. I just tried it again and it was 1200.
It is what it is.
So Excel, like, I don't know, I probably highlighted something wrong. So. Which means that's gonna change everything. So that's gonna be 60. So it's gonna be 60. And it's gonna be 20.02. So the square root. Maybe let's see. Oh, technically it would be 20.03, yeah. Yeah, we could do that, yeah, because that would make sense. 20.03, because we would round it, yeah. Nice catch. 20.03. So that 20.03 divided by the square root of 19.
In the second row, I'm expecting.
No, it's 20.
Oh, just.
Yeah, because we're not doing anything with the, then whatever this number is. 20, 29. Standard deviation. So 20.94. 20.03 and to 20.
So wait. So if it's there,
60. That's 60. This will change.
Slowly in the labels.
20.03.
oh, I get it. Look at the values. We could go on the values.
Oh.
Yeah, here's the one point.
4.47.
So it needs to be 1, and then labels. And enter 2 and just sell it for that.
Right. 4.4. Do you have this number? I can do it too.
I put -3.8. Oh, okay.
0.8. 3.89. So assume that math is right, it'd be the same answer. 3.9. That look right? That's right. Yeah. And then we'll do Cohen's D. Sense. So everyone ready to walk through it, or are you, a few people still working?
Right.
Okay. So the one that I just assigned. First, we state our hypotheses, which are the same. Are you guys still working? I can wait before I walk. So we got 77.43, or it's not equal. So next, we set the criteria for the decision. It's n-1, so significance level is 0.05. So 20 minus 1 for the degrees of freedom, n-1 is 19. We're going to find it. The critical value is 2.093 in our table. That makes sense. So
That's our T for you.
for our T statistic, and then we're gonna do our T obtained value. We're gonna compare the two. So if it's, so that's gonna be that's gonna be plus or minus 2.093 on either side of our of that. So the mean is equal to 60. Now, the way I got that is I took all of these, I summed them incorrectly initially. Then I went back and redid the math and divided by 20 values. 20 into 1200 is 60. So that's how we have our mean. So mean is 60. So then if you do the standard deviation, first subtract and square the difference of each score from the sample mean divided by n-1, then take the square root, which was 20.03. I did that right here. I took x minus m. I squared all of our values, got the sum of the squares right here, divided by n-1, which is a 20.02 or technically 20.03. And then I took the square root of that. Yeah, so this is the standard deviation, 20.03 from the variance right here. And then we go back in, and then we compare it to the null hypothesis, 77.43, to compute the standard error. We take the standard error, standard deviation, so 20.03, which was our standard deviation, divided by the square root of 20. So I got 4.48. You guys should silence your phones, please, just so we don't get distracted. Mine's on silent too. No worries. Find the T statistic by substituting the values of the sample mean. 60. State of the null hypothesis, 7.43. And the estimated standard error we just calculated. We have the standard error of the 4.48. So mean, sample mean minus the old mean, like the population, 60 minus 77.43 divided by 4.48 is negative 3.89. Therefore, we make a decision. The T is negative 3.89, so it falls beyond the critical value over here, just like this one did. It's like maybe a little bit closer, still in the rejection region. So the decision is to reject the null hypothesis because it's outside,
I forgot the negative part.
but it makes sense
Yeah.
walking through it. So the next thing is Cohen's D. And then, yeah. And yeah, it's actually pretty. So do you guys want a few minutes to, let's say 5, if you need more than 5, say something, and we can make it a little bit longer. 5 minutes work for everybody? 5? So we'll come back at like 11:23 or so. Where'd you get that? Yeah, I know. Go into chapter 6. I see what's confusing. Go into chapter 6 in Blackboard. And then you should get it. No, It's not that one, the one like right above the zero. Yeah, try that one. Is that it? No. No. Go back. No, I'll know when I see it. Go back in. Scroll down, no, stay in chapter 6, I know it's there. Oh, hold on, it's not it. And the helpful Z table is not it.
Because like the last one I clicked, it said like Z2 only. Well, I couldn't find
Click.
Did you get caught?
No, that's not.
it. Only says Z2, right?
What are the menu for?
I'll show you on my computer. So the Z table should be, don't you have a Z, like a Z table right below PowerPoint right here? Try refreshing. Because if it's on my blackboard,
Yeah, it's still percent full.
it should be on your blackboard. That doesn't make any sense. Because we're on the same blackboard. I can move it up, but it literally says Z table. Or I can email it to you guys. And then it should look like that. I'm just gonna restroom real quick, but I'll email you the detail before we start the next thing, so you guys have it.
I know.
I think the best one for this group. And the best one.
Did you say sorry?
Yeah.
No, I just like wasn't paying attention. I told you. So we can tell me.
So we'll go to the review and do numbers. So the number should be
From the book.
from the book of the 700 is all the one column. So 700, 450, 850, 450.
I'm not surprised at all.
So 450 is like.
There should be a Z table right here. Do you see it yet? Or do I need to email you? Chapter 6, I can email it. But I, right under learning objectives, it should say Z table now if you refresh in Blackboard. So download that. And then I'll come over there before we do the next thing here.
Oh,
And then keep going, and then you're gonna start to see. Like what we're talking, see, that's where that came from. So if you go up,
Oh,
that
the
was,
other one?
that was two tails combined, 0.05. that was your alpha level, and then your degrees of freedom, which was 19. We intersected those, that's where I got that from.
But I'm updating all my.
So the 3.89, I'll show you.
Yeah, every single number except that.
Okay, yeah, I can show you again. That's fine. So what I did is. So I think we're on part, you want to, I can start from the top. So we had our null hypothesis and alternative hypothesis right here. That makes sense, right? Okay. So then we just found it, n-1, so that's 19, so that's your value, 2.093. That makes sense, right? So then we compute the test statistic. So we first compute the estimated standard error. So the standard error is the standard deviation divided by the square root of n, which the standard deviation we previously calculated, which was 2.03, which I have like over here, that was all of our x minus m stuff. This is our variance, sum of the squares divided by n minus 1. And then I took the square root to get the 20.03. So that was right, 20.03, and n is equal to 20. So I took 20.03 standard deviation divided by the square root of 20, and I got 4.48 for our standard error of the mean. Then we did the t obtained value, which was the sample mean with the identity crisis minus the regular mean with no identity crisis, divided by the standard error, so 60. And that mean came from here because I took all these, I divided those by 20, right? So the mean 60 minus 77.43 divided by 4.48 is where you get the negative 3.89 from, which is your t obtained value against your t statistic. And that tells you what you're going to do, whether you're going to retain or reject the null hypothesis based on which side of the tail it's on. Is chapter 9 feeling clearer? Okay,
Yeah. I did.
good. Okay, cool. So we did that. Okay, so you guys ready for Cohen's d? Are you still working or is it making? Okay. You're good, Dave? Okay. Just remember that T table, use your textbook, or there's a Z table in chapter 6. You can download it. It's basically what the textbook looks like. So the T table is critical values T distribution with various degrees of freedom. The T statistic for a one sample T test is the difference between the sample mean and the population mean is stated by the null hypothesis divided by the estimated standard error. We just walked through that. The sample standard deviation is used to estimate the population standard deviation in the estimated Cohen-D's formula. An estimated Cohen's d is a measure of the effect size in terms of the number of standard deviations that the mean scores shift above or below the population mean stated by the null hypothesis. The larger the value estimated of Cohen's d, the larger the effect in the population. The proportion of variance is a measure of effect size in terms of proportion or percent of variability in the dependent variable that can be explained or accounted for by the treatment. In a hypothesis setting, a treatment is any unique characteristic of a sample or any unique way that a researcher treats a sample. So the formula for Cohen's d is mean minus mean divided by the standard deviation. So the above example, not the standard error, standard deviation, so slightly different. D is equal to 62 from the first one, not the one we just did, minus 72.43 divided by the standard deviation 20.94, which is negative 0.74. And then we have the table in terms of what that means. So the next thing I'm asking you to do is literally the same formula with the set of data that I just gave you. So we can do that as a group, or you can take a few minutes on your own, then we can walk through it for Cohen's d. Let's take a few minutes. I'll do the math up here too on my own, and then we'll check your answers, see if that makes sense. It's maybe my math right, Alexa, I think that's
I
right.
don't know, cause I got points, negative points.
Right. So just make sure that the brackets are correct, because first it should be the numerator. So 60 minus, hang on, I might have made 60 minus 72.43,
72?
77, that's why.
Oh,
Yeah, I could have done a typo.
I still
Possible.
got that.
60 minus 77.43, negative 70.3 divided by 20.03. Negative
Oh,
0.87.
I did 72.
Yeah,
That's the way it is.
I did a typo, sorry.
Wait, why are we doing 77?
Because we're doing the sample mean minus the population mean.
Oh, the population. I just carried it over.
Yeah. That's right. You guys do it in the back. So you should have 60 minus 77.43. For the second set of data, so that was that mean that we already had, divided by 20.03, so you already have the standard deviation, so you should have negative 0.87. Everybody on the same page with me, or do you want me to go over that? Makes sense so far? Okay. So notes and formulas. Proportion of variance is equal to the variance explained divided by total variability. That's your proportion of variance. How much variability is explained divided by the total variability numerator and denominator. ETA squared is a measure of the proportion of variance that can be expressed in a single formula based on the results of a t-test. N2 for ETA squared is equal to t squared divided by t squared plus degrees of freedom. Therefore, in this formula, t is the value of the t statistic which we had from the first one. I think it's 3.126. To find variance, we square the standard deviation. Now watch your order of operations for this to work. If you get a weird number, you're not doing PEMDAS, basically everything in the brackets, numerator, and then denominator, to make sure you're doing it correctly. To find the variance, we square the standard deviation, thus ETA squared formula. We find the value of t, so 3.26 squared plus 17. So you should be able to get 0.360. 4.36. So in this example, we conclude that 36% of the variability in social functioning, the dependent variable, can be explained, so how much it varies, 36%, or it can be explained by the fact that participants were relatives who care for patients with OCD of the treatment. So now, and you can use page 264 in our paper text section 9.4, calculate the ETA squared from the previous problem. So you're going to take your t squared divided by t squared plus the degrees of freedom from the previous problem. And then we'll walk through that. Does that make sense? Number you have. Do you have a number already?
What?
Do you have a number already?
No, I was just like, do we have to?
No, the books. It's for reference. It's for reference. I taught this course online for a while,
Yeah, we got.
which still worked, but I try to make it as simple as possible so that you would know what to do with the formulas. So there's people who work in groups, and they would come back and they talk about it. So I just try to really make it as simple as possible. It's nice to actually do this face to face stuff. I felt so weird the first couple of weeks of like last semester because I wasn't used to it. I absolutely enjoy face to face way more than just online. To know you all and see everybody, but it felt unusual because I was like 2 years of just purely Zoom. So I guess because I was so like accustomed to Zoom, like my brain wanted to think it's Zoom or something. Does anyone have a number for me? I didn't calculate that.
0.44.
Does everyone else have that? If you all have that, then I'm assuming you probably did that right. So then we would conclude that 44% of the variability, it would literally be this conclusion because we would take and we multiply it by 100 to get the percentage. Move the decimal point over 2 places. We would do that 44% of the variability in social functioning with the new group can be explained by the fact that participants were relatives who care for patients with OCD treatment. So it's kind of like how much it's affecting that shift or that change of behavior. Ready for omega?
Mhm.
Yeah, omega squared W2. Not sure why they chose W2. I feel like it does not representative of omega. Omega squared is also the variability explained by a treatment. Divided by the total variability observed. The change in the formula of proportion of variance is 1 subtracted from T2 in the numerator. So W2 is equal to T2 minus 1 divided by T2 plus degrees of freedom. So if we plug this in, subtracting 1 in the numerator reduces the estimate of the effect size. Therefore, omega squared will always give a smaller or more conservative estimate of the effect size, making it less biased than ETA squared. Using the omega squared formula, the proportion of variance for the first example, n equals 18 is W squared is equal to negative 3.126 squared minus 1 divided by -3.126 plus squared plus 17 is 0.33 of variability in social functioning. The dependent variable, so it's, like I said, it's more conservative, that's why it's at 33%. In this plan, that students for relatives of those who care for OCD. If you reference table 9.4, you can find the value of the ET scores also has a large effect size. So that table, like what it means is that table 9.4. So now before we do SPSS, calculate W squared for N equals for the other set of data. Because you should have that in front of you. I'll do it too, then we'll walk through it, and then we'll do some SPSS stuff, and then we'll jump into some more 9 and 10 stuff. Yeah, she's right. Sometimes you have two parentheses for it to know the order of operations.
That's, yeah. Okay, so. we divide it into two.
You just do one and then square, and then you do the plus and then do the- Yeah. Mhm. Yeah. Mhm.
What do you have for a number, Katie?
0.414.
Now, without checking your math, which I can totally do, I'm pretty sure you did it right because of the last one was 0.44. Now, if we all have a bunch of different numbers, then I'll walk through it if almost everybody's getting that, and that makes sense. And then it's going to be the same thing. We can conclude that 41.4, or we can just, or we can round down to 41% of variability in social functioning can be explained by the fact that participants care for OCD. And I believe that's also a large effect size too. And then we're going to do 9.6 for SPSS, which is right here. You ready for SPSS? Okay. Data set, open. Share. Okay, so what we're gonna do is, you guys can all see that, everybody? Is we're gonna click on the variable view tab right here. And we're gonna enter in health in the name column, so health. Health. Health like that. Oh, no, it's not right. We don't want that there. We want variable view. It's gonna be HALTH health. Then we're gonna make the decimal 0. Decimal 0. The variable view column, perfect health, okay. And then we're gonna enter the 18 values, which we could probably grab from chapter 9. I'm pretty sure they're all just like right here. So I think you can probably cut and paste from Word. We'll find out if this actually works in a second here. These should be those 18 values. Yeah, so if I take these and do Control C, I should be able to bring those into the data view, maybe. Yep, there we go. So data view. And then if we grab the values, I should be able to just cut and paste. Make sure you grab the first set of data, because it's not the second set there. Just make sure you scroll far enough up. Yeah, we're doing the first set of data. Starts with 18, ends with 85. You should have something that looks like this at this point. These are your values that you want to have. You can cut and paste them from Word. Does everyone have those values, or are people entering those in? The very first problem, yeah. It would still work if we did the second set of data. I just, it does matter because what I'm going to show you, like your answers won't match mine if you do the wrong set of data. If you're saying it doesn't matter in terms of like doing the steps correct in SPSS, no. But in terms of having the right answer, yes, then you want to grab the right set of data. Yeah. I don't know if I can zoom in. Like so. But if you cut and paste those from the Word document for the first problem.
Yeah, I copied it here.
Oh.
It's okay.
Or I can read them if you want. You want me to read them to you while you enter them? That'd be helpful.
I think it's okay. Yeah, that's it.
Yeah.
It's a number one.
Yeah. So you're coding variables. Variable view is like coding them, like labeling them, saying what they are. Data view is actually the raw data. Yeah. I will absolutely wait till everybody is at least to this point, just so you guys follow along with me. Are you okay? Is that making sense so far? Oh, yeah, I have. Okay, just waiting for everybody to catch up. Okay, no problem. Yep, that's it. That's exactly what we're doing. Yeah. Yeah, perfect. Make sure you know about it.
Yeah.
Yeah, I did see that email over the weekend. That was the code of eight. So we're just comparing mean values of exercise, so it's not really it has to do with just code of eight. So you wouldn't put it there underneath your, we're just looking at the variability between the sample mean and the population.
one sample, one sample. And then change your test value. Now you can just put
Now I'm saving and receiving.
First one was 44.
Yes, I'm just saving as again.
No, the first one was 0.36 and the second one was 0.4. So as long as you plug the difference, we'll probably have
There
to
you go,
register cost, maybe. Make sure you're maybe like double parentheses in the numerator.
What about side it?
Probably happens as well. Is that a whack?
First, yes, so what?
That's why it's going through. So we're just talking about the variability between the two means, like how much they vary.
Our data for this, when I submitted.
So we're talking about the
So doing
variance.
it again.
Which ones do between those two, so it's not really like projected. How much the means are there.
First.
Does that make sense?
And then I resubmit.
We're gonna do that as a class right now. So the next thing we're gonna do, I think everybody's caught up. If you're not, tell me, I can totally wait. We're gonna say, go to the menu bar, analyze, compare means, one sample t-test, move health over. And then you should just be able to click, basically, it should just be, type test value should be 77.43 right here. Our other mean 77.43. 77.43. And then we're gonna go okay. And then we should have.
Can I give us the probability?
0.936. Yeah,
No, not descriptive. Can you go to compare means?
yep, analyze, compare means.
It's right underneath descriptive.
Analyze, compare means, one sample t-test. Health, you're gonna put this, the 77.43 in here, and then you're gonna just click on OK. And then it gives you all of that. Degrees of freedom. 0.936, 0.93, that's the same. And then that is, I believe that's it for that part of it. You save that, or since we're gonna do another SPSS, you can. Yep, save file. And SPV file. Yep. And then I just have stuff to review, and then we'll do another SPSS exercise, and then we'll be on to chapter.
Put the same data. No, it's the one from the book. that they put in.
9.9, let me see. No, it's a different data set.
We should then just like save you that.
I would just save them for themselves, yeah. But it's actually pretty easy. Like even if we have to enter it by hand, it's not a lot of data. So I'd probably just save those. And then we'll do 9 as a group. This is actually just notes. So before I jump into that review, I'll let you guys save your SPSS. Maybe just like look up or tell me you're good to go. What? Yeah, just save it as a SPV file, which is your output file, and then save your data as a .sav file. And then what you're probably gonna want to do is close your SPV file once it's saved, your output file, like the file that looks like this. And then what you're probably gonna want to do in a moment is you're gonna open up a new data, just a brand new SPSS file, which I'll show you how to do in a second. We'll put some data in, we'll do one more exercise, and that'll complete this worksheet. You guys are probably still saving, right? So we'll analyze. And we're going to compare means, one sample t-test. And why it's not letting me do that, I don't know. Analyze. Oh, that's why. It doesn't like the. Change that measure that worked in the other one. It's weird. Okay. All right. And are you still saving? Are you guys ready to go? Carlos? Okay. An independent sample is a type of sample in which different participants are independently observed, one time in each group. The two independent sample t-test is a statistical procedure used to compare the mean difference between two independent groups. That's typically used to test hypotheses concerning the difference between the two population means, where variance in one of both populations is unknown. Some notes for a two independent sample t-test: for assumptions, normality, random sampling, independence, equal variance. Normality, normally distributed, that's a bell curve. Random sampling, that we're getting them randomly. Independence, each outcome or observation independent of the previous one. And equal variances, that the variances in the population are equal to each other for that to work between the two different populations, how much they vary, how much the scores vary away from each other. Therefore, a larger variance, S squared, divided by the smaller variance, S squared, will be less than 2. 4 assumptions for two independent sample t-tests are normality, random sampling, independence, and equal variances. We can add the degrees of freedom for each sample to find the degrees of freedom for a two independent sample t-test. The two independent sample t-test measures the number of standard deviations and t-distribution that a mean difference between groups deviates from the mean difference stated in the null hypothesis. The pooled sample standard deviation is an unbiased estimate for the standard deviation of the difference between the two population means in terms of Cohen's d. We just did that. Proportion of variance is calculated using the same formula for one sample and two sample independent same t-tests. Omega squared can only be computed for a test when t is greater than 1. The estimated standard error for the difference in an estimate of the standard deviation of a sampling distribution of mean differences between two sample means. It is an estimate of the standard error or standard distance that the means differences can be expected to deviate from the mean difference stated in the null hypothesis. Then we have the pooled sample variance. That's a mean sample of variance of two samples. When the sample size is unequal, the variance in each group or sample is weighted by its respective degrees of freedom. The pooled sample standard deviation is the combined sample standard deviation of two groups or samples. It is computed by taking the square root of the pooled sample variance to measure estimates of the standard deviation for this difference between the two population means. And we're doing 9.9 SPSS. So we're going to go File, New. I would like get a completely new data file. I would close your output file if you haven't already. So the first thing we're going to do is we're going to click on the variable view tab right here. So to make sure you're not on the data view, variable view, like that. And we're going to enter groups in the name column. So groups. We're going to say intake. Yeah. Good. And then we're going to zero out the decimals. Like that. Put over here for everybody watching this later, groups, intake, like that. We're going to make these 0. That. In the row label groups, click on the small gray box. With 3 dots in the values column. So you see that? We clicked on that. So label, so small gray box in the label. Labels right here. 3 dots, click on that. That comes up. The dialog, so we're going to click add. And then we're going to say 1 for the value right here. 1. We'll say okay. So 1 and then slowly like that. And then we're going to grab this and say 2. And then we're going to say fast. That. And then we're going to say okay. Slowly and fast. So that looks like this. Values, value labels, add 1 slowly. Then we're going to add again 2 fast. Then we're going to say okay. Everybody following so far? Making sense? Then we're going to click on the data view tab right here. And then we're going to enter 1 in the first 6 cells. And then 2 in the next 6 cells. So we're going to go 1. And then we're going to go 2. So you should have something that looks like that. And then we're going to enter the slow group and the group eating fast. So I'm just gonna do that right here. So group should be 1 all the way down to 6, and then 2 all the way down to 12. And then we're gonna use the table if you're following along on our text, and we're gonna enter these in. So the group eating slowly, they had 700 calories, 450 calories, 850 calories, 600 calories, 450 calories, 550 calories, and then fast groups 450, 800, 50, 700. Does that make sense, everybody? We're gonna enter that right here. 100, 450, 850, 600, 450. 550, 450, 800, 750, 700. Did do that right? 450, 800, 750, 550, 650. So we got those, and then next thing we're going to do is, everybody have this so far? We're going to click on analyze, compare means, independent sample t-test, and a sample t-test like that. Using the arrows, we're going to move intake into the test variables and group into the grouping variables. So like that, intake, and then grouping variable like that. And then we should be able to just click. Yep, and then we're going to click define groups. 1. And 2, say continue. And then say okay. And then it's going to give you breakdown. Should look like that. Yeah. Then your T, your degrees of freedom. standard error of mean, standard deviation, there's your t-test, like that. Zero. Analyze, compare means, independent sample test. Intake goes here, groups go here. And then define groups, 1 and 2, okay. Then we get our output file. Then we're just gonna save that. Yeah. And then we'll just save the file. And that takes us to the end, of that worksheet. Yeah. One sample t-test. And then you're gonna put the intake of the test variables, and then the grouping variables, the groups. Then you're gonna click on define groups. And just make sure you have 1 and 2 for each one of them. It might pre-populate. And then you click OK, and then you'll get. Yeah, it should look like this. It should be analyze, compare means, independent sample t-test. Put this right here, intake under test variables, put grouping variables here. And then you should have an option to define groups. And group 1 should be 1 and group 2 should be 2, then click OK, and then it should spit out your standard error of your difference, your mean difference, your two-tailed, your degrees of freedom, and your T, which looks like this. Yeah. And then just save the file, yeah. So that's perfect. That's perfect. So now, did you? So you should probably already did it. Is you have a output file? That's the last one. Cancel. Yeah, or save it or something like close it. That's fine, because you have multiple files. That's fine.
So for that one is gonna be the photos.
So this should be the save file and then STD file. That's fine. If your output tends to be all in one. It's probably just close it and open a new one, so it just goes to the original output. Files, it means perfect independent sample. Test, yeah, that's right. Move intake there. I don't know, we're trying to estimate effect size. You know what I think happened? I think it's because we did it wrong. So cancel out of there. Go analyze. Compare means. Independent sample t-test, perfect, yep. Now take intake and put that on your test variables first, not groups, yep. Now take groups, now go like that, now click define groups. 1 and 2, that's perfect, so just say continue. Now say okay. Save.
So all those two will go in the same file, right? The same.
If you end up having one output file with multiple. Yeah, yeah. So you'll have, so I will go through your Word document, make sure you're doing the math, the steps right. Then I'm also checking your SPSS that you're able to do the same. So the next thing would be to go into the next worksheet. How's everybody doing? We can take a few minutes if you'd like, or we can keep working whatever suits you all the best. What was that? Worksheets, okay. So I think the first worksheet was 9 and 10 review, that was really conceptual. So that should be student resources, in-class activities. And then I think that was this one. Yeah, chapters 9 and 10 in review worksheet. And then so you're basically gonna fill the chart in. So, and then this one is whether it's an independent or dependent sample. So let's see, it's 10 after. This is literally just filling the chart in. And then what I could do is maybe go over the answers with you all. So let's take 5 or 10 and I'll come around and maybe 5 or so, see how you're doing. And then I'll show you and walk you through the answers and see, compare and contrast. And then we'll jump into that last worksheet and we'll probably be either in a good spot to finish all the worksheets today, or at least be really close to the end of those. Make sense, everybody? I'll give you a few minutes to see if you can do this on your own. If it doesn't make sense, let me know. Are you stuck?
For the SPS. Or sheet. But I guess the question is for the 7.4, are we plugging in the data from the second?
I think that's what 10.4 does. You're talking about the SPS, but like the thing we haven't done
Yep.
yet, right?
Yep.
I think that's what it does, because I remember looking that up recently.
Just so we know we're plugging in the right one.
Is the present and the absent one
From the second example, from the book.
from the
present.
book? From the book.
So we are changing it from the book.
Yeah.
Okay.
Mhm. Yeah. Sometimes I use the book one, sometimes I use my own, to give you a good blend. Yeah. That's okay. So that's all that was. I gave you that. File. And then that file down. You save it as.
That's what I had.
So save as a CSV file. Put it on a separate file. Yeah, and then you're gonna open submitted to SPSS
If that's it,
as
now you
a
got like.
Excel file, and then drop down, and then the the files, and then you'll be able to run. I think that's a new setup.
Tell me if your Mac has.
Yeah, you should just download it from. Probably already have it. But it's in Blackboard. Like you can retrieve that. That's what it's around 7. So go back up.
I just add all of them in
Oh,
the
620.
one.
Take that file
That's
for
what he-
now.
we didn't- Oh, gee, then he just added all of this. That's how I got.
Now, enable edit. And you file, save as. Wherever you want to save it. So you can find it. Or, and now, versus Excel workbook. So you save type. Change that to a CSV file. I would do CSV. Yep. And then, yep, you can just save it, so you know what it is. Now we go to SPSS. File this.
Like, usually
You
it's
file.
10, 25. Oh, it's 10?
Excel. Now, file type CSV.
Oh, wait, that's his, sorry.
CSV.
Yeah,
Now,
I thought it was
now
just
find
15.
where you save that.
5, 15, negative 10.
If you're under documents, I don't know where you save it.
25.
This PC or something. Or Windows.
No, it's not.
You want to make sure you save it. So you can find it. And then you just do the steps in the worksheet, the cross tabs, and then you get a nice little upload file, chart, and you save.
I'm still doing.
Documents, maybe just somewhere where you find it. Make sure it's a CSV file. Then
The one that hit present and, in the.
Yeah. Perfect file.
This one, right? Yeah, is that it?
So,
Oh, yeah, I'm gonna confirm it with the official voice.
and
Okay.
then CSV, yeah, you have it there. You truncate it, just click through that until that's okay. Basically just change
I
the
just fell in.
format, so
Point
problem
nine.
child file.
But I put
Just click
11.88.
next, don't worry about modifying that stuff, just like.
And then you do some squares. so you have to
Now, it's gonna take a minute because
Square root all that.
now you can do the analyze cross tabs and
Square root of
it should work from where what it said in the worksheet. Analyze and I believe it's.
That's square root, I mean, right? Yes. That's the word.
Analyze script statistics.
Square each one.
And then I
That's
think
where you're
you had a job title and like this or something, but I gave you some stuff. I think I gave you some other
No.
ones. They don't have to be the same ones. I think we did
That's too
job,
cute.
whatever's on the Zoom recording, I think we did job title. I think it was gross was in, job title was in rows and I think column was gross. But
Some of that.
yeah, but I modified it in class because that's off SPSS, it's off SPSS document. And then job title's not listed. So I just grabbed some variables and I said, in the recording,
This
and then
part
when I
here,
was getting you.
when you do some of squares minus the
Let's do it.
95 squared divided by 8.
Yeah,
90.
perfect.
So it'd be this one, 95 minus 90.
Yeah.
Total.
Does it have to be one file? Yeah, I would save an SPV file with that and save file. Chapter 8, yeah, whatever's easiest. Like, what it is, that's fine. I'm not beating you guys up on like, able to save it certain ways. It's gotta be obvious what it is. You don't save them all the same, because with the wrong thing or that piece of it, no problem. So I was thinking for time, I can show you what you should have for 9 and 10, or I can give you a few more minutes. How's everybody doing on this exercise? Good. Front row. So what you should have is this is what you should have for the chapter 9 worksheet. If you grab those off the table, those are the numbers you should have. Does that make sense? Or approximately? You looked those up in your appendices. That's where that came from. Does at least this makes sense, or at least you know where to look if you don't have that, everybody? If you guys are confused, just let me know. So the next question is, as the level of significance increases from 0.1 to 0.10, does a critical value increase or decrease? And it decreases. The next one is, as the degrees of freedom increases from 8 to 120, does the critical value increase or decrease? You're literally just looking at this. That's where you're getting the answers from. Critical value decreases. Number 4 is, how is this related to power? And the answer is, as sample size increases, the degrees of freedom increase, thereby increasing the power to detect an effect. This increases power by reducing the cutoff for the rejection region. The rejection region is larger. And then, of course, similarly, as level of significance increases from 0.1 to 0.10, the cutoff for the rejection region is reduced, making the rejection region larger, thereby increasing the power. Is that making sense? And then you would have this for your chart for number 5. That was just the chart, right? 5. Following the Z and the T for one-tailed, two-tailed tests. So this would have just been in your chart. And then number 6 is, how do critical values you listed in the previous question, these, compare with those listed for the Z distribution? And your answer would be, the critical values are identical, give or take rounding, because the T distribution with degrees of freedom is infinity. That is a standard normal Z distribution. Makes sense so far, or at least mostly. So chapter 10. You ready for 10 or so? Okay. How does winning influence self-efficacy, belief in one's ability among high school students? Study 1 and study 2. Study 1 was independent samples. Study 2 was dependent related samples. Does that make sense for why? Should we walk through that? Study 2 was dependent related samples. Study 1 was number 2, study 1 dependent related samples. Study 2 independent samples. For number 3, study 1 was independent samples. Study 2 was dependent related samples. For number 4, study 1 was independent samples, study 2 was dependent related samples. And for number 5, study 1 was dependent related samples and study 2 was independent samples. And then how you got there would be based on what they told you about each one. So if, like, for example, number 5, they researched snacking between meals would only reduce calories consumed in the meal. Participants thought of the food as snack foods. On day 1, they gave a group of participants 100 kcals of food. They thought of a snack and recorded the number of calories consumed the subsequent meal. On the second day, they gave the same group of participants the same amount, and they test whether there was a difference. So these are the same people. That's why that's a dependent related sample. Study 2, they had different groups, which is why they're independent samples. Is that kind of making sense? Independent, dependent samples. You want to walk through? So if you look at so the answer for number 5 is dependent related samples and independent samples. Now why? Well, we work with the same group in study 1, so that's why it's dependent and related. And then we work with different groups in study 2, which is why it's independent. And it's a similar rationale for all of those based on how the scenario is painted. And then these right here are what you should have for those. And then if that makes sense, we can definitely jump into that last worksheet for chapter 10 and do as much of that as we can in class today. Of course, if anything I'm talking about right now needs further explanation or doesn't make sense, tell me. And it's fine if you are writing down the answers, but you should totally understand how you got there. So if you want to like write the answers down and then go back and like think through it, like how did I get to a related or independent sample? I'm totally down with that, but I want to make sure when you get to the test and you see a new example, it makes sense to you. Gentleman in the back ish, okay, good sense. So like, for example, study 1, independent samples, dependent. Why is that? Well, if we look, there's 2 groups that are separated, so that's independent, and then 2 they measure the same athletes, so it's a related sample, just at different times. So independent, usually we're gonna have like, I'd say if I wanted to look, I wouldn't do this, but if I wanted to compare like scores between men and women in different groups, or if I wanted to say, how are you all performing as students in stats at the beginning of the semester and the end of the semester, that'd be like related samples. That makes that a little more. So then I think our last thing was my institution, statistics, student resources, in-class activities, and then it should be this right here. Yeah, chapter 10 review. Okay, and a related sample. Everybody's with me so far? Okay. And a related sample, also called a dependent sample. Participants are related. Participants can be related in one of 2 ways. They are observed in more than one group, repeated measures design, or they are matched experimentally or naturally based on the common characteristics or traits. A matched pairs design, that's a review from earlier today. The repeated measures design is a research design in which the same participants are observed in each treatment. The 2 types of repeated measures designs are the pre-post design and the subject design. The pre-post design is a type of repeated measures design in which researchers measure a dependent variable for participants before, pre, and after post treatment. FY, the 2 types of designs for selecting related samples are repeated measures and matched pairs designs. In a matched pairs design, participants are matched based on the characteristics that they share. Matched pairs can be obtained either experimentally or through natural occurrence. In a repeated measures design, the same participants are observed in each treatment. 2 types of repeated measure designs are the pre, post, and within subject designs. Computing different scores prior to computing the test statistic reduces error by eliminating one possible source of error, thereby increasing the power of hypothesis test. The degrees of freedom for the related samples t-test equal the number of different scores -1. Degrees of freedom difference -1. 2 assumptions for a related sample t-test are normality and independence of the groups. So the within subjects design is a type of repeated measures design in which researchers observe the same participants across many treatments, but not necessarily before and after a treatment. The matched pairs design, also called the matched subjects design or matched samples design, is a research design in which participants are selected and then matched experimentally or naturally based on common characteristics. The related samples t-test is a stats procedure used to test hypotheses concerning 2 related samples selected from the populations in which the variance in one or more populations is unknown. A different score is a score or value obtained by subtracting one score from another. In the related samples t-test, different scores are obtained prior to computing the test statistic. For a t-test, the term error refers to any unexplained difference that cannot be attributed to or caused by having different treatments. The standard error of the mean is used to measure the error or unexplained differences in a statistical design. The estimated standard error for the difference of the scores, SM, is an estimate of the standard deviation of a sampling distribution of a mean difference scores. It is an estimate of the standard error or standard distance that the mean difference scores deviate from the mean difference score stated in the null hypothesis. Therefore, let's actually make sure that we're sharing here. Stop. Chapter 10. View. Okay, we'll give it a second to, let's open that up. All right, and let's make sure we're sharing on Zoom. Share. Chapter 10, share. Okay. So we just went over all of this. All right, example one. One area of focus in many areas of psychology and education is on understanding and promoting reading among children and adults. Suppose we conduct a study with this area of focus by testing if teacher supervision influences the time that elementary school children read. To test this, we stage 2 6-minute reading sessions and record the time in seconds the children spent reading each session. In one session, children read with the teacher present in the room. In another session, the same group of children read without a teacher present. The difference in times is recorded right here. Spent reading versus the absence. Here's our difference right here. Step 1, state the hypotheses. Okay, so we'll state our hypotheses. Because we're testing whether or not equal to or not equal to a difference exists, the null hypothesis states that there is no mean difference, and the alternative hypothesis states there is. So in all null hypothesis, there is no mean difference in time spent reading in the presence versus the absence of a teacher. Alternative hypothesis is not equal to 0. There is a mean difference in time spent reading in the presence versus the absence of the teacher. Something happens when the teacher's in or not in the room. The null alternative hypothesis makes statements about a population of mean difference scores. Step 2, set the criteria for the decision. Level of significance is 0.05. This is a two-tailed test for the mean difference between two related samples. So 8 minus 1, so we're 8. So that's 7. We go locate 7 degrees of freedom in the far left column of the t-table in C2, appendix C. Move across the column to find the critical values for 0.05 in proportion tails. The critical values for this test are plus or minus 2.365. Does everyone see 2.365 in the table? Okay. We will then compare the value of the t-statistic to the critical values. The value of the test statistic that falls either beyond the critical value, plus or minus 2.365. There's less than a 5% chance that we would obtain the outcome if the null hypothesis were true. So we'll reject the null hypothesis, otherwise we're going to retain it. Make sense? Step 3, compute the test statistic. To compute the test statistic, we compute the mean variance and the standard deviation of the difference in the scores. Compute, not computer. Compute the estimated standard error for difference and compute the test statistic. So compute the mean variance and standard deviation of the difference in scores. Keep in mind the sign negative or positive of the difference in scores matter what we compute and the standard deviation mean. So to compute the mean, sum the different scores and divide by the total number of scores summed. Sum 120 divided by 8 is 15. Does that make sense so far, everybody? Where I got that from? To compute the variance, we'll use a computational formula. That's on page 119. And you can see the table in our textbook on page 315. Sum of the squares, difference of n minus 1 with sum of the squares is equal to sum of the difference squared minus the sum of the difference squared divided by the difference. So sum of the squares is 3,400 minus 120 squared divided by 8, which is 1,600. And then for the variance, sum of the difference is equal to 1,600 divided by 8 minus 1, which is 22.857. And then we do the square root to get the standard deviation, which is 15.12. To compute the estimated standard error for the difference in scores, we substitute 15.12 for the standard difference. 15.12 divided by the square root of 8 is 5.35. And I'll just scroll so that everybody can see this on Zoom. Okay. So then we compute the test statistic. We substitute 15 for mean difference and 0 for the null hypothesis. As I came up earlier, this is the value stated in the null hypothesis. So T obtained value is mean difference sample minus mean difference population. 15 minus 0 divided by 5.35 equals 2.84. Make a decision. To make a decision,
we compare the obtained value to the critical value, reject the null hypothesis. If the value obtained exceeds the critical value, the decision is to reject the null hypothesis because it's 0.2804. And what was it up here? It was 2.6 something, right? 2.365. So 2.8 is bigger than that. And then all we have left, and we'll do whatever we can do today, because we're at the end of the worksheet, we'll have time if we don't finish it all. We do the exact same calculations with this, and then SPSS 10.4, and that takes us to the end of chapter 10, including reviewing. So we can do that together or on your own. We got about 15. Y'all think you want to give it a shot, or you want to walk through it as a group? Or you can all give it a shot, both things. I'll come around and I'll help you. And then everything's unclear, we'll walk through it on Wednesday or towards the end of the class. So that should go pretty quick. Yeah, you have a question? Or we can just walk through it if you want. Yeah, I'll come around. So start on that and then I'll come around and walk you guys through it. And I'll, yeah, so. Yeah. I just remember the answers. That's good. So all you're doing is you're looking these up. And then once you look them up, most of the answers should be kind of straightforward. I'm with you, yeah. And then it's just on the other half of it, it's just like how this marriage. The answers, I don't know if my words, I'm sure the answers for the worksheet. I would just, if you want to look backwards, I would just want to like. What was it?
You know what it means, like what it would be.
Yeah, I do have
This and what is this?
what I'm looking for. So like this one, I have that list, which I can totally share with you how to write post in Blackboard. And then for this one, the answers are right here off the table. And then what happens? Like I said, I could, what was that?
So you can reference that.
Which one? This one? But if you look at the T table, this should all make sense. Does that make more sense?
Yeah.
Okay. How are you doing in the front row? Yeah. That's the difference in scores. Yeah. Some of the squares, which would have been. Yeah.
Yeah, squared.
Yeah, I squared, not square root.
Sorry,
That's what I was
square,
throwing
I
out.
know, squares.
Totally,
rooted,
they're like-
squared.
Very related
Yes,
concepts, yes.
so squared, and then you got the 1600, and then you divide. So I did the same process.
That's what I have.
And then square root of each. Square root of 5 divided by 8. Plug that in. Square root of that, which is standard deviation of 16. And place square root of 8 to the and then plug it in 15. And then
And is that older T statistic?
So that's. like, I mean, up here,
Yeah, because,
because we use 8, it's gonna be the same critical value, 2, 3, 6, 5, did it change?
oh, that would be the same, yep, yep, yep.
So 2, 3, 6,
It's fine,
5.
yeah.
So it's a little bit.
Oh, so you're gonna- So you're gonna reject.
Right, so you're technical.
Yep. Yep.
Awesome. And I did that.
Yeah.
Yeah. Like the way that you have it laid out, which is nice, because that helps. with a lot of important things.
Yes, that's literally the last two steps, so wait, I can walk through that. That's for. There's a question over here. Or did I read that wrong? Here's the number, okay.
Wait, which worksheet is
So, So I would do, I would go over and say, and then I would go and say, because it's 4 hours.
No, the other one, hot egg.
It's doing something else, you know.
Oh, no,
Gee,
hot
the
sorry.
number.
Sorry.
Barbados.
Yeah, I think, yeah.
Okay.
Okay, but I also.
That's it.
Do you want? Oh, I'm sorry.
No,
I'm sorry.
that's-
3.82 squared and then 2 of them and then divide
Yeah,
it into
okay.
1.9 squared.
The spike goes on there.
One and then made a second one, 719. Just make sure that like it's
I don't wanna
all the
play
numerator, all the denominator. You should say. Yeah, it's you're manipulating the order of operation, which is based on mouse, but it should just be the fraction.
It's going on tonight, and yeah.
And it's all-
Not
No,
20.
because it's what it is actually 3.89 squared divided by 3.89 plus 2. So it's gonna be that it's gonna be a slightly bigger number, which is why you get 0.36.
That's like my new side,
Oh my god, that's hilarious.
Yeah, because it would have to be one to be less than
Oh, I didn't.
1 percentage of the variable. So that's probably what's happening. My guess is you're taking this square divided by this and you're adding 19 or 20. Yeah. So you take it and you take,
How do you
and
guys
you get the
do?
denominator with the 19 from that. Thank you. Yeah. So, do you want to tell me your calculations? Because I can probably do that faster with,
Yeah.
if you've already done it. Your math looked correct, so,
Awesome.
um, so I'm just gonna move this down and walk everybody through this. I don't know if we're gonna have time for 10.4. We might. Or if you guys can stay like couple minutes, we might be all right, so we're gonna take this and I just moved that all down. Standard hypotheses, there's no mean, so these should be the same. And then this should be the same because it's the same critical value. And then these numbers should be different.
Yeah, so when you add the differences of scores, the total becomes 95.
So this should be 95 and
And
this should
then
be
the answer, when you divide 95 by 8 is 11 point, I think like 11.875, but I rounded it to 11.9.
9. Okay. And then
And then the sum of the squares ends up being 29.25. And then 95 squared
95 squared divided by 8.
divided by 8, and I got 1796.88. And then we do 1796.88 divided by 7, and I got 256.70. And then you square root 256.70 to get your standard deviation, and I got 16.02. And then you get the variance of that, and that's 5.66. And then the bottom, you divide it by 5.66, and I got 2.650. And then we reject the null because it's still above.
Everyone see that? Does that make sense?
Yeah.
Or at least mostly, I hope. And then 10.4. Actually, we probably could knock out 10.4. Or we could do 10.4 next class. Why don't we do that?
Sounds good for the next class.
How about we do SPSS? Try to do it on your own. So we'll do SPSS for 10, and then we'll do chapter 11. We'll do this. We'll do worksheets. And you guys are doing awesome. Maybe we'll get through chapter 12, and then we can have more review time or more time for questions and answers and stuff. So you guys can certainly go a few minutes early if you have questions on grades, how you're doing in the class, etc. Remember, there's 870 points. You should probably have at least well into like half of them at this point. Pre-test, post-test, WebAssign. You all want that coming in. WebAssign, remember, I manually import that, so your scores will come in. The pre-test, you're going to get all the points as long as you attempt it. Don't skip the pre-test and post-test. There's a lot of points. You want to make sure you're doing those. If you've fallen behind or you're seeing blanks, it's whatever. It's not what Blackboard tells you. It's based on the syllabus. So I'm rooting for you all to do well, but you gotta have all the points.
So right now we're supposed to have like how many?
I would say probably at least a half to 2/3 of the points at this point because of where we are and what we've submitted. Was it 870? I think it was 870. I can tell you. I'm just doing it off memory.
Yeah, you can focus a little bit so we know where we're at.
We're like the second to last week.
So not everything's graded, okay, but a lot of stuff is.
I think we have like almost 100 right now.
A total of 830 points for the course. That's a grading scale. So you're gonna have, you shouldn't have 1,200 points. That'd be too high. Something's going in wrong. Blackboard. I don't think anybody does. I just looked. Everybody was all like in the 200 to like 600 range, like for the class recent. Like everybody's. So your pre quizzes and post quizzes 180 points. Those are the ones for the 12 chapters. Extra credit doesn't count as 830.
Ah.
That's why.
Does it make sense now?
Yeah.
She's like, what? I was like,
WebAssign 180 points. So you probably have some of that. Okay. We have the in-class assignments. It's actually, that's actually 70. Yeah, 70. 70 points. So that should be about 170 points, 180. And exams 300 points. So if you're clipping along, you have a lot of points. That's great. If you're like, I have only a couple hundred points, you might want to look at what you haven't submitted or if there's anything pending. But you should totally not be at like 100, 200 points. I would say you should probably be at least 300 to 500 points right now. Because we still have exam 2, we still have exam 3, we still have some web science stuff to come in yet. And then what I'll probably assign would be chapter 11 pre-test for next time. Web assign soon for chapter 10. I think I may have already assigned it. I'll double check. And then homework that we didn't finish, that won't be doing until next class period. And I can post an announcement too. Yeah.
Can I use chapter 9 post test by Zoom?
Mhm.
I think it's closed or like it's late now. But
So email me or text me if you have a problem doing it.
okay,
If it records it as late and lets you submit a score, I should still be able to see it.
okay,
If it doesn't let you do anything or locks you out, I can adjust the date
okay.
for you in Blackboard. That should be fine. Or you can send me an email or text and I'll reply back, hey, I've adjusted it. You're good to go.
Sounds good.
Anything else? Anybody else?
But I'm gonna do one of those.
Perfect. And I'll keep doing that. Usually that's helpful, right, Alexa? Like the announcements are always, okay, okay, good. So do that. And I don't know if you saw those YouTube videos. Those hopefully relying on my brother.
See you Wednesday.
See you Wednesday.
Bye.
Yeah. Hang on, let me just stop the recording, then I will absolutely answer your question.